And we're back. I think this is the last part of our unit for the test coming up. And as it says in the title, potential energy and charges. I got nothing clever to put on the front of this part. So what are we doing on this one? We're going to revisit back into the fall, potential energy and kinetic energy. We are going to then kind of go over how do charged particles have potential energy. And then how can the potential energy increase or decrease in a charged object? And again, we're just going back with potential energy and kinetic. So back a long time ago, we discussed potential energy, and it's still the same thing. Back in the fall, we said it was stored energy that can be changed into motion. And typically, we want to think that if we give something more potential, then it's able to change that into a greater amount of motion. Back in the fall, we talked about, for example, potential energy having an object having potential energy because of where it is and how far it can fall, with the idea that if it's at a greater height, then it would take longer to fall, it would have longer time to accelerate, therefore it would be going at a greater velocity. Think about this, in order for us to give an object more potential energy, we would have to do more work on it. We would have to push it. We would have to lift it to a higher level in order to get it to have more potential energy. But again, the potential energy and kinetic energy kind of work in lockstep. The reason it's got more potential energy, if you just want to think of it easily, is that it can be turned into more kinetic energy. And again, you can't get energy from nothing. And so if we get a larger amount of energy, then we had to have more built up energy to start with. Reminder about kinetic energy, that was just energy of motion. So again, the potential energy turns into the kinetic energy. So if we had an object higher up, again, it was able to fall, it'd be going faster. And so last semester, we could increase the kinetic energy by making sure it was going faster. We would also say it would have more kinetic energy if it had more mass as well. But in terms of its position, that's kind of how the kinetic and the potential went together, was where was it? So if we lifted it up higher to give it more potential energy, it could fall faster to be able to get more kinetic energy. All right, so how does all this relate to charges? Right? So as we hopefully already know, that charged particles will move when they're near other charged particles. So this kind of goes back into motion a little bit. Reminder that opposites attract and like charges repel each other. And so think about this again, those things are moving. And so as we start thinking about potential energy and tying it back into last semester, what can we do to the charges to be able to cause them to have more motion? So think about magnets, think about repelling, think about the stuff you've already talked about in terms of how much force there is between two objects. You did the PhET simulation where when the objects were closer and closer, the amount of force between them was higher. So if we take two like charges, for example, the closer they get to one another, the greater force it takes for them to push them together. Therefore, there's going to be a greater amount of force pushing them apart. And because they're going to be pushing apart and going to be going faster, then that's going to relate to the amount of energy that they have. So again, this is going to result in a greater velocity. It means that they're going to have more potential energy when pushed close together. It's going to require more effort. If you could do it, if you're able to take two charged particles and push them together, it would require a lot of energy to put them together. So then when you release them, they're going to be able to move farther apart. Right. So this is an example, a couple of illustrations that we have on here. Hopefully this makes a little bit of sense. So first thing I've got on here is that this is a positive, and the one on the bottom is also positive. So we're just kind of comparing and contrasting what happens if you take two positive particles and in the upper left, kind of have them far apart, and in the bottom right, kind of get them close together. So in the upper left, you see that they have very short arrows. Down at the bottom right, they have longer arrows. Those are indicative or telling us how much force there is. And then there's a little bar going up and down on the right-hand side that says potential energy. So the upper illustration says that's a really, really low potential energy. The one on the right is a higher potential energy. The only difference between the two is just generally, like, the only thing that was changed was how close together are they. So in the bottom right illustration, they've been pushed close together. And so again, as they get closer together, their force is going to go up. And then since their force is going to go up, that means if we let them go, they would be able to accelerate faster or to a greater degree. Therefore, when we put them together, they have a high potential energy. So rule of thumb, when you have similarly charged particles, two positives or two negatives, their potential energy is going to be greatest when they are close together. Because again, think about it, if you let them go, they're going to spread apart and go at a high rate to be able to do that. So in the upper left-hand corner, if you let them go, they would move, but again, they would not result in near as much motion as they would on the right. Therefore, there's more potential energy on the right one than the left one. Okay, so again, low potential energy, high potential energy. High potential is because they're close together. Low potential is because they're far apart. All right, so let's contrast this to what happens if there's opposite charges. Remember, opposites attract, so they want to be together. And this kind of flips around. So actually, when they're really, really close together, there's hardly any potential energy because they're already close together. The attraction, the distance, the motion they're able to have at that point is going to be really, really small. So if you got them really, really close together and let them go, they don't have very far to go. So there's not very much potential energy. Effectively, once they're together, and even if they were stuck together, the potential energy approaches to be zero at that point. Therefore, the potential energy should get greater as they're going apart if the potential energy is zero when they're touching. Let's look at how these are related. Again, the top one is the lower of the potential energy, up here where my head is, and the bottom one is going to be the one that has the higher potential energy. So this is the opposite of the previous picture that you saw. And the only difference here compared to the previous one is that we have opposite charges. On this top one, they're opposite charges. They're really, really close together. The arrows are so big they went off the screen. So that's how much force there is between the two because they're really, really close together. And it might seem like since there's so much force, there would be a lot of potential energy. But again, they're already pushed all the way close together. Again, that would be like comparing us to the Earth. We have our greatest attraction with the Earth when we're on the Earth. That's where the greatest force between us and the Earth is. As we get farther and farther away from the Earth, our attraction gets less, and the amount of force gets less as well. So, but our potential energy goes up. So, this is kind of like on the bottom right-hand picture. As we spread them farther and farther apart, that's like raising something up from the Earth. Its potential energy gets greater because they're going to be attracted to each other, right? So hopefully that's not too confusing. There's just, again, a couple of rules of thumb. Whether you want to evaluate whether the charges are positive, negative, or positive, positive, or negative, negative. And again, think about what would happen to the particles if they were kind of let go. Where is the most motion bound to happen? All right, in this last screen, I'm just kind of giving an illustration, is if we had a row of positives and a row of negatives, where would the potential energy be the highest, lowest for each of these particles? So if I took this positive charge and placed it somewhere in here, where would it have the highest potential energy? Again, it's going to have the highest potential energy closest to a like charge. The highest potential energy would be moving this proton, if this is a proton, over here to the other positive charges, because again, positives and positives are going to push each other away. And so if I could get it as close to these two middle charges as possible, it would be repelled all the way down to the bottom. So its potential energy would be the highest up here. Its potential energy would be the lowest down here, hanging out with the negative charges. And then the negative charge would be exactly the reverse. The negative charge would have the highest potential energy hanging down here with the negatives because it would want to get pushed away. And it would have the lowest potential energy hanging out up here with the positive charges. So in summary, we went through and answered all those questions about potential energy and kinetic energy. It relates back to what we did in the fall in terms of motion and just trying to predict and think about how much motion would something get. And again, evaluate whether or not you've got like charges or opposite charges and whether they're close together or they're going to be far apart.